This presentation is about numerical simulation of deep cement mixed column supported embankment. It is a case study, and the main aim of this study is to find out the most likely failure mechanism for this embankment. These are my co-authors, and we all are from the School of Engineering, Design and Built Environment from the Western Sydney University, Australia. This is the outline of my presentation. First, I will give you an introduction, then the case study and the finite element model used for the analysis. Then I will compare the results obtained from the finite element model with the case study measurements from the field, such as settlements, excess water pressures, loads applied over DCM columns and soil, lateral deformations of the ground, bending moment of columns, and the overall stability. Finally, the conclusions. We all know that embankments are widely used in infrastructure projects to provide an elevated platform. In soft ground, when embankments are constructed, settlements are very large and also instability problems can happen. So wide range of ground improvement technologies have been developed over the years to improve the bearing capacity and settlement characteristics of the soft ground. Consolidation based methods are commonly used to improve the shear strength and stiffness of these soft soils. But the problem is they are time consuming, and also in difficult ground conditions, these methods can be unpredictable. Uh, because of that, these methods can be uh, uneconomical in difficult ground conditions. And also, time restrictions in projects may be unfavorable for these consolidation based methods because of the lengthy times required for consolidation. Because of that, deep cement mixed columns are introduced as a fast track and an economical ground stabilization method to bypass the disadvantages associated with conventional consolidation based ground improvement techniques. This is the geometry of the embankment. This embankment is from the Bangbo district of Samut Prakan province of Thailand. Uh, the soil layering you can see in this picture, there is a fill material at the top, then we have 11 meters of soft clay, and then medium stiff clay and stiff clay. We have DCM columns, a 0.6 meter diameter, and spacing between them is 1.5 meters, and they are in a square pattern, and the construction is conducted in four different stages, and the field measurements were continued for 235 days. In this case, the special thing is they have not used any geosynthetics but used double columns underneath the side slopes of the embankment to reduce lateral deformations of the ground. This is a finite element model created for this problem. Due to the symmetry of the problem, we used half of the model, and we used 6 node triangular elements below the water table, that means below the fill layer, we used 4 pressure degrees of freedom at the corner nodes of these 6 node triangles. And soft clay and medium stiff clay are modeled using modified camp clay model, and all the other materials like embankment fill material, uh, stiff clay and deep cement mixed columns were modeled using the Mocoulomb model. So this is the variation of settlement with the time. You can see that settlements are increasing gradually after the end of the construction in this embankment. According to the geotechnical design standard of the main roads, Queensland, Australia, the limitation of maximum serviceability settlement should be 50 millimeters after the construction. Also, this standard specifies allowable differential settlement at the time of the design and handover to be 0.5% over 5 meters for sealed asphalt uh, surfaces. So in this case, the rate of embankment settlement after construction is about 23.7 millimeters per year. And if this embankment is assessed based on this design standard, the total in-service settlements can be a problem after few years for this embankment. The differential settlements are very low and they are not going to be a problem. This is a settlement distribution 3 meters away from the toe of the embankment after 235 days. You can see that the settlement is more than 70 millimeters, and majority of the settlement has happened in the medium stiff layer, and in this case it is 43% in the medium stiff clay, and it is about 43% in the soft clay. That reduction is due to the stiffness of the higher stiffness of the fill material above the soft clay. These are the excess pore pressures. They are very low, 1 meter below the soft clay layer, and 2 meters below the soft clay. They are one very low, and in the stiff clay layer, 1 meters below the soft clay, pore pressures are very high. The reason is closer to the surface, closer to the groundwater table, we have set up a zero pore pressure boundary condition. Because of that, uh, pore water pressures are high within the low within the soft clay layer. This is the load distribution between uh, columns and soft soil. In the figure, you can see where earth pressure cells are placed, and in this case, total embankment load is about 30 kilopascals. But we can see that soil has a very lower uh, pressure compared to the embankment load, and columns have a higher load compared to the embankment load. That means there some arching happens in this case. And if we calculate the load carrying capacity of an individual column, it is about 300 kilonewtons, and the load applied on a single column is about 10 kilometers. So if we calculate the factor of safety against vertical load carrying capacity, in this case it is 30. That means it is not a critical case. That means this embankment is never going to fail due to exceeding vertical load carrying capacity of columns. This is the lateral deformation of the ground. Lateral deformations are very high around the middle of the soft clay layer. This is the bending moment distribution for the double columns. So the bending moment carrying capacity of double columns is about 2.8 kilonewton meters based on the field testing. But the bending moment actual value is about 2.3. So the calculated factor of safety against bending failure is 1.3 for this embankment. And if we calculate the overall stability, in this case, we calculated it from the RS2 software, and it is about 3.54. That means based on the three failure modes we calculated, most critical failure mode is due to bending failure of double columns near the side slopes of this embankment. Finally, the conclusions. So in this case, The numerical simulations are carried using the RS2 software for this case study, and the in-service settlements can be a problem for this embankment, but the differential settlements are very low. The maximum lateral deformations occur away from the toe. Therefore, during an after embankment construction, additional loads may be transmitted to foundations of nearby structures, and the most likely failure mode was investigated by calculating factor of safety for failure of individual columns against bearing failure, double columns against bending failure, and overall stability of the embankment. And results show that failure is likely to happen due to bending failure of double columns near the side slopes of the embankment. Thank you.